Okay, so my name is Wajahat Chima, and I'm going to be doing homework number 5, question number 1. Okay, so we're given a random variable z, which is equal to the sum of the random variables x plus y. So we see that the probability mass function of z is f of z equals probability of z less than z equals probability of x plus y. We're just swapping it out, is less than z. Similarly, we can write that mass function as f of x plus y equals integral small fx xy xy dx dy, and the limit will be x plus y less than or equal to z. So as you can see, this is a function of both x and y. We can write this in two different ways. Sorry. So first we can either solve for x, so x less than z minus y. In this case, I'm making the x-axis the vertical one, the y the horizontal one. This will be it right here. And the probability mass function, we can write it as f of z equals negative infinity to infinity, negative infinity z minus y. We're getting that from here, this limit, f of xy dx dy. Solving it a little bit further using partial differentiation integration, we can use f of z equals partial derivatives, d dz f z equals negative infinity infinity d dz negative infinity z minus y f of xy dx dy, and that equals negative infinity infinity f of xy z minus y dy. Okay, so solving for y here, y is less than z minus x. Over here I'm using y as the vertical axis, x is the horizontal, so same graph. F of z equals negative infinity infinity negative infinity. Instead of z minus y, we have z minus x here because we're using this limit. F of xy x comma y dy dx. F of z equals d dz f z equals negative infinity infinity d dz negative infinity to z minus x. F of xy dy dx. And this equals negative infinity infinity f of xy x z minus x. We're swapping out the y for the z minus x dx. So moving on, if this is independent, we can split up the density function, and we can write this as f of z equals negative infinity to infinity f of x z minus y f of y dy. Similarly, if this is independent, we can split it up also. F of z equals negative infinity to infinity f of x f of y z minus x dx. Okay, so we were told to do this two different ways. So for the second way, we can also use the unit step function to solve. Alright, so let's start that. F of z equals double integrals f of xy x comma y dx dy, and we're using the limits as x plus y is less than z, and this is the unit step function. And since it's a unit step function for x plus y greater than z, this function will not exist. Alright, so let's move on. This equals f of xy x comma y u z minus x plus y dx dy, which equals f of xy x comma y u z minus x minus y dx dy. So we can solve this with respects to y, which equals y is less than z minus x. This over here we have x plus y less than z, and we can just subtract x from both sides, and so z minus x has to be greater, because if it's less than y, the entire unit step function would be negative and will not exist. So similarly, we get the integrals here. We have the limit as z minus x f of xy x comma y dy dx. This is similar to the method that we used first. We'll get a similar outcome. And to solve with respect to x, we can write as x less than z minus y, and also this also z minus y has to be greater than x. If it's less than x, the entire unit function step function will be negative and will not exist. So we're getting negative infinity to infinity, negative infinity to z minus y f of xy x comma y dx dy. So this is similar to the previous method that we used. We were getting the same result. And yep, these are the two methods you can use to solve this problem. Thank you for watching.